All right. So another reminder, if there's a time where I've recorded a video, because I record every one of these lectures with a few exceptions. I didn't record yesterday because we were just basically going over the portfolio stuff. If you go home and you don't see the video on there, does everybody know where to find those, right? Okay. If you don't see the video you need on there, if I happen to forget that day and not upload it or something like that, just send me an email and I'll get that and post it up there. I forgot last night because somebody emailed me, so I put it on there like at 8 o'clock or something like that. Okay, so this section is on applications of rational equations. Does anybody remember what the root word of rational is? Ratio. Okay, and what is a ratio? Ratio is just a fancy word for a what? A fraction. Okay, so these are going to be equations with fractions in them. So we know how to solve those. We learned how to solve those last week. And we're going to do applications. And usually when we apply math, it's going to have something to do with maybe a real-world problem or a story problem that some nerdy mathematician made up, which is the case with problems 8 and 9. Okay? So the key here is once we write the equation down, the equations are pretty easy to solve. It's coming up with the right equations that can be a little bit difficult. Okay, so let's start off with number 8. Let's just think about this for a second. Usually, most story problems are punctuated pretty well. So if you read them and pause at the punctuation and think about what they're talking about, you may have better luck in figuring it out. So number 8 says, the reciprocal of 10, and then it has a comma. So let's just think about that for a second. The reciprocal of 10. Well, the reciprocal means we flip it over, right? So the reciprocal of 10 would be 1/10. Plus the reciprocal of 15. That's going to be 1/15. So plus the reciprocal of 15, so 1/15, is the reciprocal of what number? Is. Now, normally when we're reading a math problem, if we say is, that means equals. Is the reciprocal of what number? Now, do we know the number? We don't know the number, so let's either use n or we could use x for that. I don't really care. Okay, again, it's good to use a variable that reminds us of what we're looking for. So on this one, I'm going to go ahead and use n, if that's okay. So if n is the number that we're not sure of, what would its reciprocal be? Well, the reciprocal of 10 was 1/10. The reciprocal of 15 was 1/15. What's the reciprocal of n? 1 over n, or 1/nth, if we wanted to think of it that way. The reciprocal of 10 plus the reciprocal of 15 is the reciprocal of what number? We're not sure, but it's 1 over n is its reciprocal. Everybody good there? Okay, any questions? Okay, at this point, this should be an easy problem. You should know exactly what to do. Don't get faked out and do something that looks like it ought to be right when it's actually incorrect. Is the answer here n equals 25? I mean, it kind of looks like, well, gosh, this is 10 and this is 15. Add them together, you should get n. Is that right? No way. You can reason your way to the fact that that's not the right answer by looking at the top. 1 plus 1 is not 1. Okay? So that should be a clue that there's something wrong there. Okay, how do we generally solve rational equations? What technique do we use? Okay, we multiply by the common denominator, or we multiply by something that will get rid of all the factors. So we have a factor of 10, which is a 2 and a 5. We have a factor of 15, which is a 3 and a 5. And we have a factor of n. So we need to cancel off a 10, a 15, and an n. And we want to do it with the smallest number or the smallest expression possible. So what's the smallest thing I can multiply by that will cancel off a 10 and a 15? 30. Okay, so 30 would do it. And I need to cancel off an n also, so I'm going to multiply by 30n. When I multiply here, and again, I showed all the work last time. Hopefully we can move fairly quickly through this. If I multiply here, the 30 cancels with the 10. There'd be a 3 left with an n. When I multiply here, the 30 cancels with the 15. There's a 2 left, so that's going to be a 2n, and don't forget the plus there. And then when I multiply the other side, the n cancels, so there's a 30 left. So this actually is pretty easy, because when I add these together, I get 5n equals 30, so I get n equals 6. Let's keep this in mind and go back and let's read the question and make sure that actually makes sense. It says the reciprocal of 10 plus the reciprocal of 15 is the reciprocal of, what did we figure out the number was? 6. You could actually check this. Is 1/10 plus 1/15, does it actually equal 1/6? If you got a common denominator here, this would be 30, right? That'd be 3/10 plus, 3/30 plus 2/30. That's going to be 5/30, which reduces to 1/6. So it does indeed work. Okay? All right. Any questions? Okay, so pay attention to the punctuation. Sometimes that can be helpful. Let's take a look at the next one. It says the sum of. Now this one's worded differently. On number 8, it started off by giving us a number, telling us what operation we're going to be adding, then another number is equal to another one. This one says the sum. We're expecting to do what here? Add. We're going to add a couple things together. Let's think of what they are. The sum of a number. Do we know what the number is? Okay. Some people want to use x, so we'll use x. Let's call the number x. The sum of a number, so we're going to be adding a number and something else. 6 times its reciprocal. Well, if x is the number, what would its reciprocal be? 1 over x. So what's 6 times 1 over x? Whoops. If you wanted to write it like this, just to make it clear, there's the number, plus 6 times its reciprocal, is -5. So if we clean this up just a tad, we'd have, let's see, 6 over x equals -5. And then how would we clear the fractions here? How would we get rid of the denominators? Okay, this one's not bad. There's only one denominator. There's only one thing that makes this a rational equation that makes this a bit ugly, and that's this x right here. So let's multiply. We get x squared, we get 6, and I get -5x. Now we take a look at this for just a second because we learned how to solve these not in this chapter but in the previous chapter. So we've got x squared plus 6 equals -5x. What do we normally do with a problem like this? Set it equal to 0. We set it equal to 0 so we can take advantage of the 0 property of multiplication. So if I move the 5x to this side, they're all positive now. And then if I write it as a multiplication problem, then I can figure this out. So if we're going to write it as a multiplication problem, that's code for we need to factor this. Numbers that multiply to be +6 combined to be +5. +2 and +3, right? So this says x equals -2 and x equals -3. Do you think they both work? Okay, well let's take a look at this. Look at the original equation. Is there anything that we know for a fact wouldn't work, McKay Roundy? Say 0.
Yeah, 0.
It's going to be 0, okay? This isn't one of those. This isn't one of those, so it's probably going to work. Now, we could take the time to run through and say, all right, I'm going to take -2 plus 6 times, what's the reciprocal of -2? -1/2. And I'm going to add those together and see if I end up with -5. That would be -2, that would be -3, and that would equal -5. So definitely this one works. If you plug in -3, it will also work. Okay? Any questions there? Okay, next up, these are classic algebra problems. And for some reason, I don't know why, but this book and Math Excel, they pick some really weird names, some weird activities. Some of the answers are just ridiculously, I mean, they're like really funky numbers, okay? That doesn't mean the problems are difficult to solve. It just means they're a little bit on the strange side. So we've got Chandra, and for some reason she is embroidering team logos. Takes her 6 hours. Tracy, she's a new employee. She can do the same job, but she needs 9 hours to do that embroidery job. Okay? But they're going to work together. How long will it take them if they work together? Now let's think about this for just a second. Because most people will look at this and they'll think, well, let's see, if it takes one of them 6 hours and the other one 9 hours, if they work together, then it's probably going to be the average of the two, so about 7.5 hours. Now, if you think about that for about 2 seconds, that seems slightly logical. If you think about it for longer than 2 seconds, that should sound absolutely ridiculous. Because unless Tracy is a complete idiot, even if all she does is hand Chandra the material or hand her thread or goes and gets her a drink, isn't that going to speed her time up? So isn't she going to be able to do it in less than 6 hours with a little bit of help? Okay. So we'll assume, Tracy's reasonably capable. Okay. Tracy may be a boy, you never know. Okay. And then embroidering may be a difficulty there. Okay. So there are a couple different ways that we can do this problem. So I want you to think about it this way. So let's talk about what Chandra can do, and then we'll kind of use this to understand why we set them up this way. Let's say we give her 1 hour. What fraction of the job will Chandra get done in 1 hour? Just Chandra, no help or anything. Takes her 6 hours to get the job done. If we give her 1 hour, what fraction does she get done? 1/6. If she does it for 2 hours, she gets another 6 done, so that would be 2/6. 3 hours, 3/6. That's a half. She'd be half done if we gave her 3 hours, right? Okay. So what we want to look at here is, what is her hourly rate? In 1 hour, she gets 1/6 done. So she'll get 1/6 done the first hour, another 6, total of 2/6, another 6th, another 6th, another 6th, until 6 hours go by. That would be 6/6, or 1 complete job done. So let's talk in terms of this. Hourly rate. What fraction of the job does the person get done? What fraction do they get done in 1 hour? So let's talk about Chandra. What is her hourly rate? 1/6. Okay. Let's talk about the helper, Tracy. She's going to help out. What is her hourly rate? 1/9. Okay, now, together. Okay, well, let's back up and think about this. The reason we said it was 1/6 for Chandra is it took her 6 hours. So her hourly rate was 1/6. Took Tracy 9 hours, so her hourly rate was 1/9. Do we know how long it takes them to do it together? We don't. But what could we use to represent that? X. Well, if I took how many hours it took and just did the reciprocal to figure out the hourly rate for each one of them, what would I do for the hourly rate together? 1/x. So if I take Tracy's hourly rate, Chandra's hourly rate, and add it to Tracy's hourly rate, shouldn't that equal their hourly rate together? And then let's focus on this for just a second. Isn't that an easy equation to solve? It is. Okay? Now, that's not the only way to solve this. If we're going to finish this off, here's what we do. We'd multiply by, let's see, I need to cancel off a 6, a 9, and an x. 18x. So that's going to be 3x. Multiply here, that's going to be 2x. And multiply here. Lo and behold, we end up with a nice, easy equation. Doesn't have any fractions in it, and it's a piece of cake because we add these together. 5x equals 18. So that means x equals 18/5. Now, what does that mean? 18/5. 18/5 what?
That's how long it takes.
That's how long it takes. And what's the unit of measurement for time here? Hours. Okay, so that's going to be hours. Now, the good thing about this is, normally when we're doing story problems, we get to choose the best way to write this. In algebra, we leave things as reduced and still improper fractions. On this, we'd probably say something like, how about 3 3/5 of an hour? Or how about 3.6 hours? Or better yet, you could say 3 hours and, what would that be? 36 minutes, 3 hours, 36 minutes is what it would take him.
Yes.
Good? Okay. If it's a story problem, choose a good way to explain what your answer is. I'm not sure what MathXL asks you for. Yeah?
That was my question. It's like, what Math
So this is a copy from Math Excel. I think it's problem 6, or it's really a lot like problem 6. Probably won't have the exact numbers, but it'll have the problem outlined like this, and then it'll say it'll take them this many hours and this many hours. So answer it maybe in, fractions or decimals first if that doesn't work, or maybe view an example before you go through and do the one that they ask you to. Okay, everybody good there? Okay. All right, ready to move on? Okay. I think this is the easiest approach for these. Again, it's not the only one. If you'd like to see another way to solve these, maybe in the long run is more applicable, come and see me. I'd be happy to show you. All right, so let's read this one. So we've got George and Steve. Good old American names. George can cut and split a cord of wood in 3 fewer hours than Steve can. Does anybody know what a cord of wood is? None of you are going to win Jeopardy at this rate. No one heats their home with wood? See, when I was a kid, growing up poor in Idaho, we had to go gather wood, go up in the mountains, gather wood, come home, split it. So that's what we do all winter. What's that? Oh, that's right. That's right. You're lucky. A cord of wood is a stack of wood that's 4 feet wide, 4 feet tall, and 8 feet deep. So it's roughly, it would be a stack of wood roughly the size of this desk up here. That's what a cord is. Okay? It's a measurement for volume. Okay? When they work together, it takes them 2 hours. How long would it take each of them to do the job alone? So compare this setup with the previous one. We were told how fast Chandra could do it. We were told how fast Tracy could do it. We were not told how long it would take them to do it together. This one's different. We don't know how long it takes George. We don't really know how long it takes Steve, but we know Steve is, let's see, does Steve take longer? Or, yeah, Steve takes more time, right? Okay, if you read that carefully. Then it says they can do it in 2 hours together. So we're going to do the same thing. We kept track of Chandra, Tracy, and together. So here we're going to keep track of George. We're going to keep track of Steve. And we're going to keep track of together. Now, do we know how long it takes them together?
Yes.
It takes them 2. So I'm going to take that and I'm going to figure out their hourly rate together. If we gave them an hour, they'd get half of it done. Is that right? Okay, now, we need to come up with an expression here. George can split a cord of wood in 3 fewer hours than Steve. So I don't know Steve, but I do know that George is 3 less than that. So how would I write this? S minus 3. Then I'm going to take this, flip it over. That would be 1 over S. That would be his hourly rate. If I take this and I flip it over, this would be 1 over S plus 3. Are there any questions there? And what do I do with these 3 expressions?
Wait.
Oh, S, sorry. Thinking ahead. I apologize. Okay, good there? That explains all the funny looks. Any questions here? Okay. Once I got these 3 expressions, hourly rate for Chandra, hourly rate for Tracy, and hourly rate together, what did I do with the 3 of these? Put it into an equation. I added the 2 people together and said that would be their rate together. So this is going to be 1 over S minus 3 plus 1 over S equals 1/2. Okay, are there any questions there? Okay, watch. Could I have done 1 over G plus 1 over G plus 3 equals 1/2? Could I have done that? Yeah, because this would have been 1 over George. This would have been 1 over George plus 3, so that's 3 hours longer than George, right? And then still 2 hours, so 1/2 would be the hourly rate together there. Okay, if I did this one, that would solve for George. If I did this one, this is going to solve for Steve. We have to plug in both of those answers. Let's go ahead and find them. What do I need to multiply by?
2S times S minus 3.
Okay, I need to cancel off a 2. Everybody agree with that? I need to cancel off an S, and I need to cancel off an S minus 3. So can I just put a minus 3 here? No, I need a completely separate factor of s minus 3. So when I multiply here, write down what you get. I'll write it down in just a second. Multiplying with this first term. What is it? 2s, just plain old 2s. When I multiply here, okay, plus, we've got a 2 and an s minus 3. I'm going to write it like that. We can, if you can distribute through at the same time, that's fine. And when I multiply here, I get s and s minus 3. Now, are there any questions? That should be the hard part. Once we get to here, these are problems we solved in the last chapter. So this is 2s plus 2s minus 6 equals s squared minus 3s. What do we need to do now? Combine like terms and move everything over to the same side. So I'm going to do this. I'm going to subtract 4s and cross those off. And I'm going to add 6 and cross that off. Why am I moving everything over to the right side? Very good. Ari said that. Leading coefficient is positive. So I have an s squared, I have a minus 7s, and then I have a plus 6. Now, why s? What are we looking for? When we get an answer to this, this is going to be Steve, right? It's going to tell us that answer for Steve. So I'm going to factor this. Easy to factor. Two numbers that multiply to be positive 6 combined to be, let's see, negative 7. So that's going to have to be negative 6 and negative 1, right? Which means s is either 6 or s is 1. Now, let's take a good look at this. We haven't done anything algebraically wrong, but let's read in the context of the problem. Is there any way Steve could take 1 hour? No, because together it took him 2. Okay, so that's one reason. And the other reason would be, if Steve took 1 hour, according to the algebra here, how long would it take George? Negative 2. Doesn't make any sense. So we're going to cross this off. So Steve is 6, George is 3 less than that, so that's going to be 3. Okay? And if we had solved this guy up here, we would have ended up with g equals 3. Okay, are there any questions there? Sure? You can be guaranteed you're going to find problems like this on the test. You can be almost guaranteed that you're going to find problems like this on the final exam. Okay, these do not go away. Okay? All right, so flip the page over. I mentioned when we ran into problems like this before that these also will not go away. Yeah?
Just a question. So it's okay for the George to take 3 hours even though there's an S minus 3?
Yeah, because if Steve is 6, George is going to be Steve minus 3, so that's going to be 6 minus 3. Okay? Does that work? Okay. All right. So these problems where we've got boats going upstream and downstream, airplanes flying with the wind and against the wind, stuff like that, those are going to come up over and over again. Almost guaranteed you're going to see these on the exam. Nearly guaranteed you're going to see one of these on the final exam. Does anybody remember how we set these up so we can keep track of everything? Distance equals rate times time. So we're going to set up a chart, and the chart's going to look something like this. We're going to keep track of the distance, the rate, and the time. And once we have those three things, we're going to write an equation, D equals RT. Now, in this situation, we've got this. So the speed of the current in Catamount Creek. So why do they have to come up with a funky name like that? It's 3 miles per hour. Sean is in a kayak, and he's going 4 miles upstream in the same time it takes him to kayak 10 miles downstream. How come he can go further downstream than he can upstream? Because the current's with him. And remember, we made a big deal about that. When you figure out what the rates are, you've got to have these in the right order. So here's what we're going to do. We're going to do upstream and we're going to do downstream. Now, upstream. Do we know how far he went upstream?
Yes.
How far?
4 miles.
Careful. Upstream. 4. Do we know how far he went downstream? 10. So we're going to fill that in right there. Now, it says the current is 3 miles per hour. That has something to do with how fast he can go. Now, Sean's here, he's paddling away. So we can call this paddling, we can call this the boat, whatever we want to call it. But remember, it's going to be the boat plus the current or the boat minus the current. It's not the current minus or plus the boat. Okay? So in this case, I'm going to call this paddling. So when he's going upstream, it's going to be how fast he can paddle. Are we going to add or subtract the current? Subtract it because he's going upstream. So that's going to be P minus 3. If P minus 3 is upstream, how do we represent downstream? P plus 3. Do we know anything about the times?
Same.
Okay, notice that it says in the same time. So if I use a T for this one, I'm going to use a T for this one. Now, if you can solve this a quicker way and show algebraic work, that's great. If you can solve it in your head, that's fine, but you're not going to get any points unless you can show algebraic work, because we're going to hit problems that you cannot solve in your head. Can't even construct how to put it together, but if you rely on the algebra, you'll be able to do it. So let me show you what we do at this point. This is exactly the same thing we did with the other problems that were a completely different structure. We wrote the equation, distance equals rate times time. So this would be 4 equals P minus 3, make sure that's in parentheses, times T. And then this one's going to be 10 equals P plus 3 times T. Now if you go back and look at your notes, we did exactly the same thing. And once we got here, here's the hint. This is what we do on every single one of these. Find something that's easy to solve for here. Now in both of these equations, what's easy to solve for? T. So if I take this one, 4 equals P minus 3 times T, and I solve for T, I get T equals 4 over P minus 3. If I take the other one and I solve that for solve that for T, I end up with 10 over P plus 3 equals T. Now, if we take advantage of the fact that they said the time going upstream was equal to the time going downstream, or if I just flat think, my gosh, this is a system of equations and I need to solve it, what is this set up for? 2 techniques for solving systems of equations. Substitution or elimination. What is this set up for? This is set up for elimination, for substitution. So I'm going to take 4 over P minus 3 and set it equal to 10 over P plus 3. Okay, this happens to be a special type of rational equation. It's called a proportion, and we can solve this by doing cross products. I can multiply these two together like this and put the answer here. And then I can do these two together and put the answer there. Okay, you may have seen that before. That will work every time. It's the same thing as solving or multiplying by something that will cancel off both denominators. Okay, the net effect is the same. Questions? So this is going to be 4 times P plus 3 equals 10 times P minus 3. So we're going to have 4P plus 12, 10P minus 30. I'm going to move the 4P over, so that's going to give me a 6P. I'm going to move the 30 over. That's going to give me a 42. Let's see. Divide by 6. I end up with P equals 7. What did P stand for here?
Speed.
How fast he can paddle, right? How fast can he paddle? 7 miles per hour. Okay. Any questions there? Yeah.
So if, say, like math itself throws this out, if it says, maybe it says right there, but if it said like 4 kilometers, 10 kilometers, and like 3 kilometers per hour, do we have to put kilometers, or do they have the units for us in that
I think you do have to put the, well, it depends. I mean, some problems it may, sometimes problems it may not. On a test, I wouldn't give them to you, so I'd be used to figuring it out before you look at, gosh, did they just give me the units? Okay. Maybe view an example before you do the problem. Okay, any questions? Okay, and for you AP US History people, Steve Dietmar, why they give his last name, I'm not really sure. You could Google him and find out if this actually happened. It takes 1.5 times as long to go 72 miles downstream in his boat as it does to return. So it doesn't use quite the same words there, but if he went downstream and he went back, wouldn't his distances be the same? Okay. If the boat cruises at 30 miles per hour in still water, what is the speed of the current? So we're going to do the same thing as we did just a second ago. We're going to keep track of the distance, the rate, and the time, come up with a distance, rate, time equation, and then see what we could solve for in each of those. So we're going to do up and down. What was the distance upstream? 72. And downstream? 72. They're both the same. Okay, it tells us how fast the boat goes. What it doesn't tell us is the speed of the current. So remember, it's always the boat or the airplane or the paddling or whatever it is, plus or minus the airstream or the current or whatever that is. So this is going to be 30. We're going upstream. We're going to go slower because we're going to subtract the current. And going downstream, not only are we going to go 30, we're going to add whatever the current gives us. So that's going to be plus C here. Okay, this one's kind of interesting here. Does it say how long it takes?
Sort of.
Sort of. Let's figure this out. Takes him 1.5 times as long to go 72 miles upstream. So it takes longer to go upstream than it does to go downstream. So I think the easiest thing to do would be to say, well, we don't know what this time is, but let's call that t. And this is longer. How much longer? 1.5 times as long. Now, if you want to do 1.5, that's okay, but we're going to have fractions in this problem, so we might as well think of this as a fraction. Let's do 3/2 t. Isn't that the same as 1.5 times t? Yeah. What? You could add another half of t, but that would be 1.5 t either way. Good? Okay, if you're convinced you've set up the chart correctly, then the rest of it shouldn't be confusing because it's a story problem and you shouldn't get a brain freeze or anything like that. You should just be able to say, hey, look, it's distance equals rate times time. 72 equals 30 minus c times 3/2 t, and this is going to be 72 equals 30 plus c times t. And then we stare at these two equations for a second and we think, is there a variable that would be pretty easy to solve for in each one of these? T. Okay? And that's going to be the case, I think, on nearly every single one of these types. So on this problem, here's what I'm going to do. This is going to be, let's do this one first, because this one's pretty easy. This is going to be 72 over 30 plus c equals t. If you have to, do it in parts. I'm going to write the work. The work would look like this, 30 minus c, and then I'd be dividing by 3/2 equals t. Is this the way we'd want to leave this? No, because we don't want a fraction on the bottom of a fraction. That has a name. What is that called again? When you have a fraction on the top or the bottom of a fraction? It's called a complex fraction. And we don't leave that fraction on the bottom. What do? Flip it over and we multiply. So this is what we end up with. I'm going to flip this over. That's going to put the 2 on the top and a 3 on the bottom. So here's what I've got. Let me get rid of these lines so I've got some space here. I've got 144 over 3 and 30 minus c. That equals t. And I've got t equals 72 over 30 plus c. Is everybody okay with that? And clearly, what is this set up for? Substitution. Set up for substitution. So we're going to go ahead and finish this off. So we're going to take 144 over 3 times 30 minus c, set it equal to 72, 30 plus c. That's a factor, remember. If you want to multiply this by, or do cross products with this, that's totally okay. I'm going to go back to that technique that we typically use that works on every single one of these equations, regardless of how complicated. I'm going to multiply by something that will cancel off a 3, a 30 minus c, and a 30 plus c. I mean, the net effect is you've got 144 times 30 plus c, and over here you've got 72 times 3 times 30 minus c. Now, I'm going to let you finish solving that. It's a pretty easy equation to solve. The numbers get fairly large, but the answer works out to be pretty nice. Okay? All right. Give you a couple minutes to work on that. Grab your calculator if you need to. Get an answer. Check with your neighbor. See if you got the same answer. If you did, then you're probably in pretty good shape. Yeah.
So, would you multiply both the top and bottom by 2/3, or just the entire equation?
Right here?
Yeah.
No. Okay. So, no. Let me see. Let me show you this. What if it were 72 over 3/2? I'd take this and I'd flip it over and multiply. That would put the 2 on the top and the 3 on the bottom. So I'm not making, I'm carrying out the division with the fraction. I'm not trying to make it some other equivalent fraction. If I multiplied the top and bottom by 2/3, that wouldn't help me out at all. I'd just put the fraction on the top. Yeah.
So, since the distance is the same, could you just set them equal to each other with the distance?
Elaine asks a good question, and we're going to deal with that in just a second. Some of the numbers do get kind of ugly on here. I apologize for that, but the principles behind the problem are the same.
Does that have to be a whole number?
Not always. 6480, right? And then this is going to be minus, what is that? Is that 216? 216c. So if I move these over, I've got, let's see, minus 4320, 2160. And over here, got 144 plus 216, 360. So this is 360C. Well, let's see. Does it look very promising? I think it does. If we take 2160 and divide that by 366. What's that? All that work for 6. I mean, it's really frustrating when you do all that work and it's 5. I mean,
Even worse when it's 0.
and let's see, what were the units here? It was miles, so that's going to be miles per hour. Okay. Any questions there? Okay, take a quick look. Once we get to, well gosh, if we just looked right here, looked at the two of these equations. This says 72 equals this stuff and 72 equals this stuff. So if they're both equal to 72, couldn't we set them equal to each other?
Yeah.
Watch what happens if we set them equal to each other. I get, let's see, 30 minus c times 3t equals 30 plus c times t. And if I distribute through, I get, oops, that's a 90t minus 3ct equals 30t plus ct. Is that right? Oh yeah, let me throw the halves in there. Where are we here? 3 halves. So we'll divide that by 2 and divide that by 2, right? Okay, either way, take a look at this. How many variables are there? Okay, so the whole point of doing substitution or elimination was to make an equation that has how many variables? 1, so you can solve it. So you can set them equal. This is still a true equation, but the problem is it's got still 2 variables in it, and furthermore, it's got terms with t in it and terms with kind of a new variable, c times t. Okay, that gets to be a bit of a mess, yeah.
When you're not when you distribute through, but before that, you just divided by t then.
divided by t right here? Sure. Mhm. And then you'd be solving for c, right? You can do it that way also. Okay, any questions? Sure? All right. Tomorrow we're going to do 2 sections, but they're both pretty easy. One's on formulas, the other one's on dividing polynomials. It's a pretty easy type of division. And that'll be it. Thursday is the review. So if you haven't already downloaded the review, I would download that so that you can come on Thursday with questions to ask. And then come Friday ready to take the test. Remember, if you've got anything late to turn in, it's got to be turned in by the time we take the test. Okay, have a great day.